So we've already heard some good discussions today about the new HCV antivirals and how they might be used in the future to eliminate hepatitis C virus in Canada. But there's a lot of things that are going to need to be done in order for this to be successful. And one of the things we're interested in at the BC CDC is distinguishing two populations that are affected by hepatitis C that will need to be managed in different ways. So on the one hand, we have our incident infections or new infections, which are really a result of ongoing HCV transmission, which primarily occurs in people who inject drugs. And in this population, obviously, the primary goal is to prevent ongoing transmission, and potentially we can use treatment as prevention. On the other hand, we have our prevalent or chronic infections, which are associated with a high level of morbidity and mortality and occurs primarily in baby boomers, and this is a population that we're going to need to deploy treatment to. So at the BC CDC, we have a method already that we can use to identify a subset of incident infections. So at the BC CDC, we test over 95% of people in British Columbia. And if someone comes in and they get tested, they may be negative for HCV and then come in later on and get tested and be positive for hepatitis C. So using this strategy, we can get an approximation of when that person was infected, obviously sometime between point A and point B. So this can allow us to identify a subset of recent transmission events or incident infections. But unfortunately, there's only 15% of people that have a previous negative test result available. Most new diagnoses have an unknown infection timing. So one thing that we're looking at is trying to determine whether we can use sequencing of hepatitis C virus and molecular phylogenetics as a way of maybe distinguishing some of those incident from prevalent infections. So as you may know, hepatitis C evolves quite rapidly during infection within a patient and throughout the population. And if we can take these sequences, we can integrate them phylogenetically to try to determine how the virus changes and evolves and interacts in the population. And lots of people are now looking at ways that we can use time scaling and apply those to phylogenetics as a way of determining when different transmission events or important events in the epidemic have occurred through looking at different samples taken at different times and using a molecular clock. So we hope to use this as a way to look at a big picture of how the HCV epidemic is evolving over time in BC, and also as a way of determining when transmission is occurring. And studies are showing that we can use these phylogenetic studies as a way of mirroring kind of what's going on using enhanced surveillance data. So the major goal is to develop molecular tools using sequencing and applying this at a systematic way to the population as a way of distinguishing incident and prevalent infections on an ongoing basis, hopefully at the time of diagnosis. This would be the ideal goal. So this involves a lot of sub-goals, and it's just involving a lot of sequencing and doing phylogenetic analysis of these, and then going and trying to look at clusters of closely linked transmission events. And these may be related to ongoing transmissions that are occurring and allow us to determine kind of who's transmitting to who and where can we target prevention strategies. And then we're also working on determining ways to time scale these phylogenies to really determine which infections are recent. We have some of this at a poster that's going to be up today. And then another strategy that I can't really go into is that we want to use deep sequencing to look at the variation of hepatitis C virus within one patient to try to determine whether they might be at the beginning or the end or later stages of infection. So this is kind of just a model tree to show you what we want to do on a much grander scale, which is to scale the different patient samples to the times they're collected. So that's at the tips of the trees. And then what we're really looking for is these recent transmission events that cluster closely together and have occurred recently, and we may be able to deploy prevention strategies to actually prevent ongoing transmission through these transmission clusters. And then I just wanted to point out the patristic distance is a term I'll use in a few slides, which is just the distance between two sample patients on that tree, and the smaller that distance is, the more closely linked the infections are. So we're focusing on sequencing 2 regions. We've so far done mostly the polymerase of the virus, the NS5B region, and then we're also in the process of sequencing another region which was developed by our collaborators in Australia. And this consists of the core protein, the envelope 1, and the hypervariable. So this has some more variability compared to the region that I'm going to talk about today. So far we've sequenced about 596 samples from 576 patients of people that were diagnosed at the BC Centre for Disease Control in 2011, and they were all these ones were determined to be RNA positive. So 18 patients from this set have serial samples in 2011, so they were taken at different times, and we can look at the change in the virus sequence over that time point to get an idea of how much change we expect to see during that year, I guess. And then these are divided into 3 categories. We have our 2011 seroconverters. So those patients are acute at the time that we sequenced them. They were determined to test positive for the first time in that year. And then we have a group that are more prevalent. They seroconverted prior to 2011. And then the majority, 361, are first-time positive, so we don't know when they were infected. This is just a giant phylogenetic tree showing all of the sequences that we've done and incorporated some sequences from GenBank. They group by the subtypes of hepatitis C and, in the majority that we have are genotype 1A and 3A, which are the ones that are most predominantly spread through injection drug use, and then some in 1B, 2A, and 2B, and a few others in there as well. This is just zooming into the tree to show you kind of what we're going to be looking for. So on the tree in red, we have tips of samples from same patients. So you'll see really closely linked samples from one patient. And then we can plot the distance between the samples from those same patients. And here we see that there was about a max distance of 0.0175. And then we can apply that cutoff to see if there are samples from different patients that are actually as closely linked as if they came from the same patient. To determine if these could potentially be transmissions or really closely linked infections. So this is just summarizing what we do if we apply a similar distance to the entire tree. We get about 31 clusters of really tightly linked infections. We have one larger cluster that's in the middle. I tried to highlight in a bit lighter color. Most of them are in 1A, and then we have a few closely linked transmissions in 3A and 2B. And so now we're moving on to repeating this with the core HVR1 region and using time-scaled phylogenies to estimate the timing of the clusters. Most of these are obviously going to be recent because they were sequenced in 2011, and because they're so close, it probably occurred quite recently. And then another thing that we want to do, you're going to hear from Brendan Jacka later this afternoon, who's going to talk about some intravenous drug user cohort studies that are from Vancouver, and he's done similar sequencing. And so we might be able to integrate our sequences and link some of their risk factor data that we have from those cohorts to some of the clusters that we have in the province. And then just a couple quick slides from one of our collaborators at the CDC Atlanta, Dr. Yuri Kudiakov, who has some similar interests as us in looking at incidence and prevalence using sequencing. And so this is just an integration of some of our samples and the national US HCV sequences, which show a pretty tight intermixing of sequences from BC and the US. And then this is just a quick glimpse into how we want to use deep sequencing to distinguish early stage infection from later infection. So these are 2 different trees from 2 different patients, and each tree has samples from 2 time points. There's blue versus red. So we think this is more of a chronic infection where you have a bit of a diversity in the sequence within that single patient, and you can see how that changes across the 2 time points. Whereas this is expected to be very early in infection where the sequence is really tightly clustered and hasn't yet expanded within that patient. And then we also have a poster at CASL which explains some of the things that we're trying to do with this. So overall, we hope in the future to be able to apply sequencing as a strategic way for designing some public health programs at BC CDC, and ideally would be able to apply this at a really large scale and use cluster analysis to try to further understand the transmission dynamics in the population and generate kind of a really big real-time map of what's going on with HCV infection in British Columbia as a way to both track and maybe distinguish some incidents from prevalent infections And also it could be a tool for measuring the effectiveness of public health programs. If this is ongoing, we can kind of see how treatment is able to prevent and slow the spread of infection. So a lot of people are obviously involved. It's a really big goal. A lot of people involved with this. Dr. Malcrachin is obviously the brains behind all of the operation. And then thank you to NCRTP for letting me present my work here today.